Okay, welcome everybody to the last day of the third Black Hole Microstructure Conference. Unfortunately, it will all be over, but not before a few more very interesting talks. And for today, Ben Krabs will first start us off by telling us a little bit about scrambling in the rotating BTZ from the CFT perspective. Ben, it's your go.
Okay, thank you. Well, first of all, thanks to the organizers for organizing this very nice conference and for having me. Oops, let me see how this works. All right. So in the previous edition of this conference, I derived the curve that I'm showing now. So we were computing out-of-time order correlators in extremal BTZ geometries and in associated microstate geometries. So these were 4-point functions. 2 operators were inserted at some early time, 2 at some late time. And the time difference is delta t, which you see on the horizontal axis in the picture. On the vertical axis is the iconal phase, which determines the OTOC. And the purpose of the talk today is to show you what is the CFT origin of this curve. So I'll start with some broad motivation about quantum chaos and black holes. Then I'll briefly review the bulk computations that led to this curve for the OTOC. Then I'll talk about CFT computations for 2D CFT on a line, which corresponds to a boosted BTZ black brane. And then I will be talking about CFT on a spatial circle, and I'll be focusing on rotating BTZ black holes. And finally, I will discuss the extremal limits of the previous situations. So black holes are chaotic objects, and chaos manifests itself in several ways. First, there is the relaxation to thermal equilibrium, and then there is the sensitivity to initial conditions. So you all know the Lyapunov exponent from classical chaos. In quantum mechanics, if you work in a semi-classical regime, you can approximate the Poisson bracket appearing here by a commutator. You square it and then take a thermal average. The squaring is to avoid cancellations. And this measures how a commutator squared grows as the operator W evolves in time and spreads over the system. There's 2 exponential behaviors that one has in this system. First of all, at late times, there will be an exponential saturation, which corresponds to Ruel resonances, and which, under the ADS-CFT duality, corresponds to quasi-normal mode decay of an associated black hole. And second, there is transient Lyapunov growth, which happens at earlier times. And this corresponds to redshift, and which grows exponentially if you have some observer falling towards the black hole. And this exponential redshift is precisely the exponential that you see here. One thing to notice is that it's precisely the temperature or the inverse temperature beta that appears in this exponential, whereas the exponentials of corresponding to the saturation or the quasi-normal modes are typically proportional to the temperature, but up to some factors of order unity that depend on the details of the geometry. Okay, so here is the commutator squared. If you work out what it looks like, you find that the non-trivial behavior corresponds to the out-of-time order correlator, where you have a V, a W, a V, a W. So as you can see here, this is not the usual time ordering that one usually considers. All right, so the question that motivated this work was the following. If it's true that the Lyapunov growth is really determined by the surface gravity at the horizon, so reflects what the black hole geometry looks like at the horizon, you might ask, well, what happens if we replace the black hole by a microstate geometry, which is horizonless. Now, a complication that we had to face is that most microstate geometries that have been constructed were for extremal black holes. And those have 0 temperature. And remember that the exponential was determined by the temperature, so that seems to go away. So what we did was to compute out-of-time order correlators for extremal black holes and for associated microstate geometries. As I mentioned, the result I showed at the previous edition of this conference, and now I will zoom in on to the CFT origin of it. Okay, so let's now briefly review the bulk computations. So it turns out that because of the non-standard time ordering, the 4-point function can be naturally written as an overlap of 2 states. One is easily represented at early times, 2 wave packets coming in from along the horizon in these eternal black hole pictures. The second one is easily represented at late times. And if you compute the overlap of these early time and late time states, you see that you have to compute a 2-to-2 scattering amplitude.
Sorry, can I make a comment or ask a question before
Sure.
going to this detailed computer? I mean, it seems to me and to other people that the Lyapunov exponent is not related to the horizon, but rather to the behavior of the photon sphere. Will you arrive at this conclusion, or you disagree with this?
I was planning to say a bit about that in the panel tonight, but I would say that I disagree with it.
Okay.
Yeah, but maybe if it's okay, I would postpone that to the panel. I think there are, I think this Lyapunov exponent that you and your collaborators found had to do with the instability of the photon sphere, but as far as I can tell, it looks different from the Lyapunov exponents that appear in the out-of-time order correlators. But if it's okay, I would suggest discussing it later.
Okay, thanks.
Yeah, okay. All right, so to compute this 2-to-2 scattering amplitude, one can use geodesic approximations in appropriate regimes. In that case, the normalized amplitude can be written as exponential of I times the iconal phase I was mentioning before. This iconal phase is determined by the interaction between, on the one hand, a shock wave created by one of the geodesics, the geodesic of one of the infalling particles, with the stress tensor of the other geodesic, and vice versa. Okay, so here is the linearized Einstein equation you have to solve to determine the shock wave. And the result for the iconal phase is Newton's constant times Mandel's time S. And because of the blue shifting that happens near the horizon, I seem to lose my cursor. This gives you the exponential with the temperature 1/β in front of the time difference. So this was for a non-rotating black hole. We did the same for rotating black holes, and in particular for extremal black holes that are maximally rotating. So here is the metric for a rotating BTZ black hole. You have an inner horizon R- and outer horizon R+. These are related to conserved quantities like the mass, angular momentum, temperature, and an angular potential. The case of extremal black hole is where the inner and outer horizon coincide. And what will be important for what follows is that if you want to look at the Euclidean continuation of this geometry, of course, you rotate T to imaginary values, but then you also have to rotate the angular potential to imaginary values to keep the metric real. And that you can do by choosing the inner horizon radius R- to be purely imaginary. So this metric can describe either a BTZ black brane if the coordinate phi is taken to be non-compact, or it can be a black hole if you take it to be compact. and both versions will appear in this talk. All right, so here is the curve again that I showed you before, and which I want to reproduce by doing CFT computations. So to say a little bit more about it, there is an average cubic growth of this iconal face, and superposed on that is a sawtooth pattern. And the sawtooth is composed by a longer period of quadratic growth and then a short period of exponential growth. So these are the features that I will show you how to reproduce.
So can I ask you something? What is the period of this sawtooth pattern?
Yeah, so that's the time it takes to go around the circle in the CFT. So it has to do with gravitons, or more particularly the gravitational shock wave winding around the black hole several times before interacting with the other geodesic.
Is it like a scrambling time, or is that a different time scale?
No, it's much shorter than the scrambling time. The scrambling time will be, I will come to it, but the scrambling time will be the time where this curve caps off and before there is saturation by quasi-normal modes decay. But I will talk about that in a bit.
Okay, thanks.
All right, so one more thing to make the link with the microstructure theme of this conference. What we also did was then, after we had this result for the extremal BTZ black hole, we compared to specific microstate geometries called 10N superstrata, and people much more competent than me have reviewed this in detail before in this conference. So I will limit myself to this picture. The only thing you need from this is that if this parameter A went to 0, this cap would go away and there would be an infinitely deep throat corresponding to the extremal BTZ black hole. But because the geometry is capped off, you can ask, well, what is the effect of this on the OTOC? And in short, what we found is that usually, meaning unless you take the left moving temperature to be huge, that the OTOC behaves precisely the same in this superstrata geometry than it does in the extremal BTZ black hole until the scrambling time. So as long as this growth pattern persists, we didn't see a difference between the microstates and the extremal BTZ, except in for extreme choices of parameters. All right, so in the rest of this talk, I will focus on the black brane and black hole geometry, so I will not directly come back to the microstates, but I'll say a little bit more about that in the panel tonight. Okay, so now let's move on. Yes.
What was the scrambling time in that last slide? In terms of the parameters of the superstrata?
Well, it's the same as in the extremal BTZ black hole, and I will show it later. So it's probably easier to wait a couple of slides and you will see the formula.
Okay, fine.
I'm sorry, Ben, and this time I might have missed it. Did you take any particular values for this A, or your similarity between the extremal black hole and the microstates was for all A?
Yeah, we took the minimal value of A. But
so it has to be very long for them to look similar.
Well, yeah, we took the minimal value that you can take, but unless you take this left moving temperature to be huge, there would be lots of room to shorten the depth of the throat. But yeah, the short answer is we took the throat as deep as possible.
But you're saying somehow, even if you made it shorter, there wouldn't be significant departures in the OTOC. Is this right?
Well, at some point there would be departures, of course, but okay, maybe let me see if I have some formulas I can show. Okay, let me, I have it as a backup. These are the ratios which would have to be order 1 if you wanted to see an effect. So there is this number, and there is this number. And you see that like all the parameters on the right-hand side, except for the okay, I'm going to call it left moving temperature. I switched conventions compared to my backup slides. But you see that all the parameters like the N1, D5, the conformal dimensions, which we're taking to be large, then some UV regulator, everything is trying to make the this ratio large compared to 1, while if you wanted to see a difference, it would have to be smaller than 1, say, or order 1. And similarly for the other ratio here.
Okay, thanks.
Okay.
Can I also ask a quick question?
Sure.
What is the minimal value of A? Like what determines what can be the minimal value?
Okay, I don't know it in terms of A, but the A had to do with the angular momentum for which the minimal non-zero value was 1/2 in this superstrata business.
So in this,
the translation to A, I don't know by heart, but I'm sure others can fill me in there.
So in this fixed superstratum, there's one minimal value of A, and then in another, there's another one. Is that the
right? So A is proportional to some angular momentum, so it's discrete, and there is some smallest one you can take to have a superstrata.
So the ratio A over B is actually 1 over n1/5. It can become then 2, 3, 4, 5, 6, 7, and the angular momentum becomes 2, 3, 4, 5, 6, 7. So essentially, the more you increase the angular momentum, the more A over B changes from 1 over n1/5. But the A over B ratio, which is I think the one which is the dimensionless number in this problem, is actually 1 over n1/5, and that's important for this.
But then, so how when you set a black hole limit, this is not you go out of the
strict limit. I think it's just A goes to 1 over n1/5, and you know that's small enough.
Okay.
So
good.
I think I don't know.
Yeah. So to take the black hole limit, you would have to set it to 0. But the minimal superstrata we took was corresponding to this angular momentum 1/2. Okay.
So just to understand, you still need the scaling with n1 and 5 of the. I mean, if you take it 1 or 2 or 3, it doesn't matter. But still, the throat length is scaling with n1 and 5 in this.
That's correct. Yes.
Okay. Thanks.
All right. So let's move on to CFT. Let me first review what was known about, or some of what was known about CFT computations of OTOCs before. And that goes back to a paper by Roberts and Stanford. So we're working for simplicity with conformal weights that are large compared to 1, and we take them to have a hierarchy among themselves. Here is the OTOC, where there have been some imaginary time shifts. I will say a little bit more later about why that happened. But it turns out in order to implement the time ordering properly, it's easiest to introduce some imaginary time shifts, which you could view as some regulators, and which at the end of the computation, you may or may not want to take away after smearing the operators appropriately to avoid UV divergences. The result of this normalized OTOC took the following form. And if you look at this expression, you see 2 things. First of all, if you look at really large times, where the 1 here is subdominant compared to this exponential, you see an exponential decay, which is determined by the temperature 1 over beta times the lighter of the 2 conformal dimensions. And this corresponds to quasi-normal mode decay in holography, and you see is determined by the temperature times something theory dependent, namely the dimension of the operator in this case. The other thing is that if you apply an expansion in 1 over c, so you assume now that 1 is large compared to this exponential term, then you can go to the following line where you see the early time Lyapunov behavior of the OTOC. And if you go to the commutator squared, you take 1 minus the real part of this, and you will find something that grows exponentially. So the scrambling time, okay, the formula I have is for this case. Sorry, Emil, but okay, we can come back to the other case later. In this case is the time for which the second term becomes of the same order as the one, and you see that it depends on the spatial separation of between the operators v and w, and it also depends logarithmically on the central charge of the CFT. And I should have said that I'm always working for large central charge because I'm assuming that I have a holographic 2D CFT.
Ben, could I ask a small question about the regulators epsilon I that you talked about?
Sure.
So they are supposed to be small, right?
Yes.
So I'm just looking at, let's say, the first long expression on the slide. If I take the epsilons to be small, then the epsilon ij's are also small, right? Because the ones cancel in the... So then if I look at the right-hand side of the first big expression, then it's actually going to 0 in that limit.
Yes, that's true. So what you... Okay, so you also see that the operators, there's two V operators, which are, well, which would have been coincident if it wasn't for these regulators. So it's normal that if you make them completely coincident, that there will be UV divergences.
Very good.
So what you really want to do in principle, if you really wanted to push the calculation till the end, which I'm not going to do, is you would want to smear the various operators over a certain region, which you could take the thermal scale or some other scale that you want to introduce. And after you've done that, you could take away the regulator. So that's what, in principle, you might want to do physically. What is usually done in this type of computations is that you just leave the regulators explicit and you keep them in the final result. But you keep in the back of your mind, if you wanted to do something physical with it, you would have to smear and then remove them.
Okay, very good. Because my worry just was that if something has Euclidean stuff in it, and Euclidean stuff is important, then one gets confused about whether this was a Euclidean answer just analytically continued to Lorentzian. But if in principle it can be done completely Lorentzian, then that's important. Right? Then you're really seeing Lorentzian structure on the black hole side somehow. So you're saying you could do this completely without any eyes if you really wanted
to? Yes, it can be done. It's not like I've done it myself, but
that's fine.
Yes,
I understand.
That's the lore.
Okay,
right.
Thanks.
Okay, so this was for like a CFT at finite temperature. Now, since I will be talking about extremal black holes later, I will also mention some results in vacuum, which of course is 0 temperature. So for that, you want to take the inverse temperature to infinity. You cannot directly do it on the formulas I had on the previous slide, because I was implicitly assuming that the time separation and the spatial separation were large compared to the inverse temperature. So if you want to do it, you should go back at the exact expressions, then send beta to infinity, and then focus on times large compared to the spatial separation. This was done again by Roberts and Stanford, and the result is very similar to what we had before, except that the exponential that we had here is replaced by a quadratic growth. But otherwise, everything is the same. And they coined this behavior slow scrambling because it's power law instead of exponential. So if you set beta to infinity, it's not just that the exponential becomes 1, is that the exponential gets replaced by this power law growth if you do it properly. All right. So I will be interested in slightly more complicated situations where we look at a CFT dual to rotating BTZ. So this corresponds not to a thermal ensemble with the same temperature for left and right movers, but to an ensemble with different left and right moving temperatures. Namely, the left moving temperature is well, the inverse temperature beta times 1 minus the angular potential and 1 plus the angular potential for the right moving inverse temperature. And okay, we assume that the CFT is defined on some circle with some radius L, and the spatial coordinates I'm going to denote by sigma. And then you can perform the cylinder to plane map, where you exponentiate in a way that depends on the left and right moving inverse temperatures. And note that if you wanted to do this in Euclidean 2D CFT, as I told you before, the angular potential would be purely imaginary, and Z bar would be each other's complex conjugates. So for what follows in Lorentzian signature, I'm going to use a convention where omega is positive. So that means that the right moving temperature is the smaller of the two. So an extremal limit would correspond to setting beta r to infinity. Okay, so first I will tell you the prescription that we used. So first of all, in the exact Euclidean 4-point correlator, the ordering of operators doesn't matter. The ordering starts to matter when you continue to Lorentzian correlators, because those are multi-valued due to branch cuts. And well, so different operator orderings give different results, and you can select a desired operator ordering by appropriate imaginary time shifts. I will give some formulas on the next slide. Now, we will be using conformal block expansions. And once you introduce conformal blocks, there is an additional multi-valuedness that is introduced, even in Euclidean signature, where the exact result would not have multi-valuedness. And that's because the blocks themselves are multi-valued, and it's only the full sum of the blocks that would reproduce the single-valued exact result. So if a correlator, which could be Euclidean or Lorentzian, is approximated by, say, a single Virasoro block, which we will do, then the result will depend on the chosen channel. And the prescription we will use, building on earlier work that I mentioned here, is that for each choice of a possible channel, you first perform the Euclidean computation. You then continue to Lorentzian signature with the desired time ordering, which will be an OTOC in our case. And then the prescription is that you have to select the channel that gives the maximal contribution. There was some confusion about this in some of the previous work. If you don't do it, you get unphysical results. So in formulas, you introduce the, so first you set the Lorentzian time to 0. You introduce these Euclidean time shifts. And for the OTOC, well, basically the ordering of the operators is determined by the ordering of the Euclidean time shifts. So for the OTOC, we want to take the epsilons to satisfy this relation, so that the ordering is really the one I wrote down here. Then you continue towards Lorentzian time t. You will meet, you may meet some branch cuts depending on the operator ordering that you chose, and then you have to maximize over channels. So to do the computation, you use the cylinder to plane map I mentioned before. So here I just plugged in the various insertion points. And then we will use Virasoro block decomposition, which was also used in like the early results by Stanford and Roberts and other papers. Okay, so C is the OTOC. Here is a sum over conformal Virasoro blocks labeled by dimensions of primaries. Eta and eta bar are the conformal cross ratios. In the Euclidean section, there will be each other's complex conjugates. And here are the expressions for eta and eta bar. And so the approximation that is then often made is the identity block approximation, where we restrict this sum over conformal blocks to the identity block, which is the Virasoro block corresponding to the units operator. So it contains a stress tensor, products of stress tensors, derivatives, etc. And okay, importantly, this identity block has branch cuts. I will show the formula on the next slide. And this branch cut runs from eta equals 1 along the positive real axis to infinity. So in the Euclidean plane, because of the multivaluedness I mentioned before, there will be monodromies. And physically, if you take the two V operators and you take the two W operators, and you take the two W operators and you move them such that one of them goes in between the two V's and then comes back and the other one doesn't, then you have crossed this branch cut for both eta and eta bar. So that's the multivaluedness that you get from the restriction to a single conformal block. And it can also be viewed as a choice of OPE channel that you use. Namely, are you going to contract these W's directly, or are you going to contract them along a path that moves in between the two V operators? So that corresponds to the various channels I mentioned before, and I will have to do the computations for all possible number of times I let this W circle the V, and then take the result corresponding to the dominant channel. Okay, then there will be, so after I do the Euclidean computation for a given choice of channel, I have to do the Lorentzian continuation. And you can easily check that if you start on the Euclidean section, so Lorentzian time equals 0, and you move towards the future light cone, you cross the light cone here, and when you cross the light cone, you cross the horizontal axis here, and then depending on the details, you may cross it either across the branch cut or where there is no branch cut. So for instance, if you cross the t equals sigma line, you see that because of the choice of ordering of the epsilons, you can check that eta will be larger than 1. So that one will cross the branch cut and eta bar will not. Whereas if you cross the other diagonal line, it will be eta bar that crosses the branch cut and moves to a different sheet. So here is the same story with some formula. So this is the explicit expression for the Virasoro identity block. So if we take T to be large compared to the spatial separation of the V and W insertions, and also large compared to the left and right moving temperatures, then the conformal cross ratios take these exponential forms. Going to another sheet means that you multiply 1 minus eta by this exponential of minus 2 pi I times k, where k is some integer. And so we're going to be interested in large times. So that means from this formula that eta will be close to 0. So the question is, what does this block reduce to for small values of eta? And importantly, we're not just asking this, say, on the principal sheet, because on the principal sheet, everything would be simple, right? You would be dominated by exchanging the identity operator, which is a disconnected contribution where you contract the V's, you contract the W's, and that's it. If you go to other sheets, then you get a much more non-trivial structure where in the OTOC, which is this product of left and right V naught, you get not just one, but one minus something that goes like 1 over eta, which grows exponentially. So if you do these monodromies in the Euclidean plane, then eta and eta bar will remain each other's complex conjugates. So if you take eta across the branch cut, you will automatically also take eta bar across the branch cut. And that means that if you apply a monodromy, the sum of k and k bar will always be 0. And in the Euclidean version, the result is maximized, as you can see from these expressions, when k and k bar are both 0. But I'm going to be interested in the Lorentzian results, more precisely within the future light cone. And in that case, well, either k or k bar will cross the light cone and will therefore cross the branch cut. And so the sum of the two will be equal to 1. And you can see from the formula that the result will be maximized either when k is 1 and k bar is 0, or when k is 0 and k bar is 1. And so we have to check which of the two gives the larger contribution, and that will be the channel that we choose. So here is the result. So in formulas, so I'm restricting to the future light cone. So T will always be large compared to the absolute value of sigma. And then depending on whether T is smaller or larger than this sigma divided by the angular potential, you get either the left moving or the right moving temperature appearing in the OTOC. And here is the 1 over c expansion again. I've made a drawing to illustrate this a bit. So we're going to fix the spatial separation sigma between the V and the W insertions. And then we're going to evolve towards large times and see what happens. And you see if sigma is negative in my convention where omega was positive, then you first are in this region where there is no exponential growth, and then you go to the region where you have the slower of the two Lyapunov exponents. If sigma is positive, you first enter the regime of faster exponential growth set by the left moving temperature in my conventions. And then you transition to the slower right moving Lyapunov growth. So at sufficiently late times, it's always the slower of the two that wins. So let me make a few comments. Most of these computations, I should say, were done in a nice paper by Halder, except for the issue that one should maximize over channels. And it was pointed out in a paper by Mazet and Sharoshi that this should have been done. And okay, we have done it in detail, and we find this result from the CFD. As I mentioned already, at late times, the slower of the two potentially Lyapunov exponents is realized. The faster one can appear as an instantaneous Lyapunov exponent at intermediate times. And in that case, the faster one, which well, you can see here, means that the growth is faster than the temperature 1 over beta. So that's an instantaneous Lyapunov exponent that might appear to violate the chaos bound by Maldacena, Schenker, and Stanford. But really, that bound only holds for the thermal ensemble. If you want to work in a rotating or a boosted ensemble, as in this case, you should do the derivation again. You will find a different bound, and this instantaneous Lyapunov exponent will saturate the modified bound, as far as I can tell from the papers where these things were discussed. And this is some earlier work along these lines. And okay, I should also say the 1 in these previous expressions corresponds from the identity global block, which just means the disconnected contribution. and the Lyapunov exponential comes from the stress tensor global block.
May I ask a question?
Sure.
The formula that you arrive at in the end are symmetric under the exchange of V and W, while you started with an approximation where HW was much larger than HV.
Yes, that happens after you do the 1/c expansion, because indeed in the full identity block result, the HV appears as the exponent and the HW appears in front of the exponential. But if you do the 1/c expansion, then at least in the first term, the two H's combined appear in a symmetric way.
Okay. And this was the second question. So you're assuming that HW and HV are much less than C. I mean,
I think I'm doing that. I'm not sure if it's needed, but yes, it doesn't. They can be much less than C. There's no problem. That should just be large compared to 1.
Okay. Thanks.
Yeah, but yeah, in the expansion, indeed, I assume that the second term is small compared to the 1, and how that is arranged, I don't care so much. If you want to arrange it by taking sigma very large or by taking C very large or in some other way, I'm not sure if it matters too much.
Let me make my question more precise. At the very expression, the beginning of the expression is symmetric under the exchange of V and W in a sense. There shouldn't be any
in this case it is, but if you go back to this expression, for instance.
No. I mean the object that you're computing, and you're computing with various approximation to start with, it is essentially symmetric under the exchange of V and W.
The first term in the 1/c expansion, so this term is indeed symmetric, that's correct. If I went to later times and I was interested in the quasi-normal mode decay, for instance, then V and W would appear in a rather different, well, then that appear in a different way if there is a hierarchy between them. Then the smaller one will influence the quasi-normal mode frequency, and the bigger one will not. But indeed, for this early time behavior, they appear symmetrically, even if there is a hierarchy between HV and HW. That's correct.
Okay, thanks.
Okay, so that was all for the boosted ensemble. So CFT on a line. Now I will compactify the spatial circle in the CFT, which means I will go to a holographic system dual to a rotating BTC black hole, which is the more relevant context if you want to discuss microstates as well. Okay, let me first give you the strategy in words. So the intuition from the holographic computation is that when making the spatial direction compact, so when going from a black brane to a black hole, you had to make the gravitational shock wave periodic, and that you could do by using a method of images in the bulk computation, and that's indeed what we did. Now, if you go to the 1/c, order 1/c contribution, which we've just been discussing, then that contribution arises from single graviton exchange. As I mentioned, it comes from the global block of the stress tensor. So that's the CFT counterpart of single graviton exchange. So we should ask ourselves, at least if you're interested in this first term, about global blocks of the stress tensor. Okay, there's people in the audience who know much more about this than I do, so let me just tell you what I hope to have understood from that literature. So you can consider the stress tensor global block, and it can be written, for instance, in ADS or in Euclidean BTC. It can be written as a so-called geodesic Witten diagram. A geodesic Witten diagram is almost the same as a conventional Witten diagram, except that you're not integrating the bulk interaction points over the whole space-time, the whole bulk, but you're only integrating it over geodesics that connect boundary insertion points. I will give you a picture on the next slide. And so the claim is that these geodesic Witten diagrams, that they correspond to the global conformal blocks in the CFT. And this goes back to very old papers from the 70s. And more recently, it was found out in a number of papers that these old purely CFT computations could be given a very nice ADS interpretation. There's also interesting links with bulk reconstruction, HKLL formulas, etc. Now, once we have that intuition of how to think about the CFT formula for this global conformal block, then we can think about, okay, so how can we extend this to a torus as opposed to the cylinder? So a Euclidean BTZ for a CFT on a line corresponds to a cylinder, well, a filled cylinder in the bulk. Now we want to turn this cylinder into a torus. And the intuition is that the OPE part, which corresponds to this geodesic connecting two boundary points, if these boundary points are close together in the relevant channel, that shouldn't care about whether you compactified into a large torus or you didn't. And the only thing that should care about the periodicity that you introduced is the analog of the graviton propagator. And so, because that's a bulk propagator, and because the BTZ, Euclidean BTZ black hole can be viewed as a periodic identification starting from the BTZ Euclidean black brane, you can apply a method of images to that. So let me just show you a few formulas, sorry, a few pictures instead of that. So here you can imagine having a cylinder where the circle is the Euclidean time direction. Euclidean BTZ would be this filled cylinder. These are the 4 insertion points. In Euclidean signature, the V's would be close together, the W's would be close together. This is meant to represent a geodesic, same here. And then in green, there is the bulk propagator that connects arbitrary points on both geodesics, and then you have to integrate the endpoints over the two geodesics. Then to go to the torus, the idea is that you just glue the two ends, well, you just glue the cylinder into a torus. You will have the same contribution that you had on the cylinder, but now there will always also be contributions from the bulk propagator, either in a bulk sense or in the sense of HKLL CFT operators that are dual to bulk operators. And you can wind around this torus this circle direction arbitrarily many times in either direction. So there will be a sum over some integer that will come in. So now let me take you back to the picture I had before to see which of the Lyapunov exponents will be the relevant one, given a spatial separation and given a time separation. Well, now, okay, for the time direction, nothing changes, but now given a spatial separation sigma, I will have to, because of this method of images way of constructing this torus propagator as a sum of cylinder propagators, I will have to look at values of sigma that are shifted by integers times the length of the spatial circle. So for a given sigma, there will be an infinite number of sigma minus delta L's, sigma minus delta N's, which will all contribute. And so for each of these, I will have to see for a given time which will contribute to the exponential growth. And it's clear that for a given Lorentzian time t, there will be this range of possible values of sigma minus delta L that will give the slower Lyapunov growth, and there will be this range that gives the faster Lyapunov growth. So in the end, when I sum over delta n, I will get a number of contributions with slow Lyapunov growth and a number of contributions with fast Lyapunov growth. Now, if omega is strictly between 0 and 1, so we're not in the extremal limit, then both of these regions will grow linearly with t. So once you do that, you get this sum I called the ones that give the left moving Lyapunov delta NL, the ones that give the right moving Lyapunov delta NR, and I didn't bother to compute the precise ranges or to display the precise ranges. There's order T terms that contribute in each of the two sums. And for late times, the result is well approximated by the bulk computations for rotating BTZ that were done by Mezey and Shiroshi. In the bulk computations, the implicit approximation was made that an infinite number of terms contribute. And that's because the shockwave profiles are much easier to compute if you put them at the horizon as opposed to away from the horizon. But it's clear that doesn't matter because we have some geometric series here. So whether or not you include the terms from some large value of NR to an infinite value of NR is not going to make a big difference for the sum. That will be crucially different if you go to the extremal limits, and that's because there, as I will show later, if you were not careful about this, you would find nonsense. Okay, let me move on to the extremal limits. I will be very brief about that. First, so we want to take omega to 1 to have the maximal rotation. We take the temperature to infinity while keeping beta left finite, so beta r goes to infinity. And then the result for the OTOC to order 1 over c will be the following. It's very similar to what we had for non-extremal rotating BTZ, except that the right moving component doesn't have Lyapunov growth anymore, but it's replaced by the power law growth that we would also have in vacuum, which is quite intuitive because what you did is taking the right moving temperature to 0. So at late times, where it's always the lower line that wins, we will have slow scrambling. And just one more slide, I think. Okay, so now let's go to CFT on a spatial circle in the extremal limit. In that case, we will, similarly as before, have a sum over the delta n's where the left moving Lyapunov growth applies, and then a sum over the delta n's where the right moving power law growth applies. And you might remember from the picture I had before that in the omega to 1 limits, this right moving region was getting squeezed. So there's many more terms contributing on the left than on the right. And okay, if you do the computation, wait, okay, no, I think I got that backwards, sorry. If you do the computation, you see that there's order T terms that contribute to this latter sum. And since each of the terms grows like T squared, if you have order T of them contributing, you get a growth of order T cubed. So that's the average cubic growth that I was showing you before. Now, why do we have this sawtooth pattern superposed on this? Well, the reason is that the number of copies contributing doesn't grow continuously, but it grows discretely. So once there is a new one that enters the left or the right window, it will jump discretely. And that's why if you look more microscopically, you see that there is a sequence of quadratic growths and then very short periods of exponential growth. And that's precisely the result that I showed you at the beginning of the talk. So I think I've run out of time, so I will stop here. Thank you very much.
Congrats. Ben, I have a few more minutes. There were a few questions during the...
Yeah, but it's fine. I reproduced what I wanted to reproduce, so I think we can move to questions if there are any more.
Oh, okay. Okay, that's good. I see Nico already has a question, so...
I was applauding and I inadvertently put my hand up. No, it's very, very nice.
Oh, so you don't have a question. Okay.
Emil
has one though. Emil, go on.
Yeah, I was wondering if you had an interpretation of this alternation between sort of left moving versus right moving contributions? Because I would have thought if something was scrambling, it would sort of scramble as some admixture of the left movers and right movers. I mean, there's sort of pictures that came from these old calculations of Dassen, Matur, and Kelvin-Malsain of sort of throwing something in, and the graviton, splits into a left mover and a right mover in the CFT. I would have thought that okay, the left mover, starts scrambling with whatever it scrambles with. Well, left movers and right movers start scattering. So why is something somehow splitting into left moving things, doing what they do, and right moving things doing what they do, without somehow being some kind of mixture of both of them?
Yeah. Okay, so I'm not sure if in CFT language I can tell you more than what I've said already, but I can maybe give you a picture in the bulk language. So let's see if that helps. So there, the iconal phase came from the interaction between two infalling geodesics, right? And so there's if you look at the shockwave profile, there will be it will have a spatial profile, which will have to be periodic. So you can think of it as some sequence of growing and decaying things, and then you should remember that you are in a rotating ensemble, so the geodesics will move around, and so what you find is some overall exponential growth that is set by the overall temperature of the system. And then because you are moving in this spatial landscape, you will run up and down the hills. And so if you look at the total time dependence, there will be like periods of moving up and periods of moving down. And so this is the alternation that gives the two things from that point of view. From the CFT point of view, I don't know if I can give more intuition than I've said already, so I'm not sure.
Okay, thanks.
Samir also has a question.
Yeah. Okay. Yeah. So first, let me just comment on what Emil was just asking. So in the CFT, the left and right movers collide in those old calculations, but when they collide, that's the point where they leave the ADS region, right? Because that's for the emission. So if you're only working with the ADS part of the domain, then the left and right actually are factorized. So at least in that approximation where we were working at that time, the left movers didn't interact with the right movers unless it was to leave the CFT and enter the flat space. So I don't know, that may be relevant to the previous question that Emil was asking.
Yeah, can I say one more thing about that? So I wonder if it's relevant that we are on this other sheet because of the OTOC. But no, I guess once you've mapped it to a problem with to a scattering problem, I guess you got rid of the OTOC, and then you are discussing a genuine scattering problem. So okay, I take it back. Yeah.
Yeah, I think that the factorization may just be the fact that you're keeping one conformal block, right? If you add up over many conformal blocks, then CFT correlators, even without now the flat space part, let's forget the flat space, just in a CFT, you have to take mod squares and add them. But if you keep one conformal block, it will always be factored. So the left-right interaction comes only at that step. Okay, good. So let me then also ask, but I was just trying to understand what you have on the slide up here. You did say that the number of terms contributing to the sum jumps, but I think it went by a little quickly for me. I didn't know which terms there were, so I'd like to understand better why they are jumping. And also I wanted to ask, in case you were here in Sean Hampton's talk a few days ago, he also gets a sawtooth pattern for something, and I was wondering, and that's also because something goes around the circle and hits again, around the circle, hits again. I was wondering if it's something similar.
Yeah. Okay, let's start with the first question, for which I think I do have an answer. The second one I'm less sure about. So Okay, maybe I should. Okay, so we have these operators v and w, right? And one of the two was inserted at 0, 0. The other one was inserted at spatial coordinates sigma and time coordinates t. And we take these to be time-like separated from each other. So if we had a CFT on a line, so before doing the compactification, T and sigma would correspond to one point in this plot, and depending on where you land, it would be the left or the right moving temperature that came in. So now, what we have now after compactifying is that effectively you should add images where if your physical insertion was at sigma on the line, you should also look at an insertion at sigma plus the length of the circle and so on. So you have an infinite number of those. And so you should, so for each of these contributions, you should look at this diagram and see where you find yourself. So for most of them, you will be in this gray region, which is boring because that's the Euclidean space-like separated regime where there is no exponential growth and where you're just dominated by the identity, by the disconnected contribution. So the interesting ones are these yellow and blue regions. And you can see that there will be a number of discrete dots that will correspond to discrete values of delta n that will be in this yellow region, and a number of discrete dots in this blue region. So now if I continuously change t, so I move this array of dots up or down, you will see that at some discrete times, there will be one of the dots that moves across the separating line between the yellow and the blue region. And so that's when one of the contributions jumped from one OPE channel to the other. And so those are the times at which there will be one of the terms that doesn't contribute on the right side anymore, but on the left side. So that's the discreteness that comes in.
Okay, thanks. I think that's very nice, because I think that sort of looks to me like what Sean and Ben-Guo were finding in their paper. Of course, if they're around, they should comment as well. But so let me just see if I understand. It's just because if you have a compact cylinder, spatial cylinder, then if you just follow the iconal approximation for some kind of a first approximation to something, operators do tend to go around and they can come around like this. So you get multiple passes at being able to interact with somebody. And so the longer you wait, the more chances there are that you could also use these other iconal peaks. And so all of them contribute something.
Yes, at any given time order, n of them contribute. And actually to come back to the thing I said before, so when omega goes to 1, this line is squeezed with a diagonal line. Now you should be more careful because it will not quite be squeezed. You have to be more accurate. So, but it will be the left movers that will have like an order t number of contributions. So that's what I was mentioning before on my last slide. And the left movers will have like only a few contributions, and but anyway.
Okay, great, thanks.
I see Rodolfo had his hand up.
Oh, okay, thanks. Hi, Ben, thanks for the talk. I had a question about the part where you consider the CFT on a line, right? So if I understand that's then, as you are showing, is a cylinder because the time direction is compactified to get the temperature, right? So I could just take the correlator and do a double Vic rotation, right? Interpret the compact direction as a space-like direction. And then I would have this 4-point correlator just as not a thermal correlator, but correlator in the vacuum. Right?
Yes, in global ADS, right? In the bulk,
in global ADS, yeah. So those correlators with light operators are at the holographic point, in the supergravity point, are known. So in principle, one should be able to use those results to find and do the double Vic rotation to find the OTOC without the block approximation.
Okay.
And it's more difficult to do the interesting case where it's actually not torus, right? Where it's not an line.
Yeah. Okay. Thanks. Okay. Thanks. Yeah.
Yeah. I'm happy then to discuss about this. I mean,
yeah. I'd be very happy to. And then, okay, if anybody has good ideas of how to get from the cylinder to the torus, so I think we convinced ourselves that at the level of the analog of the single graviton exchange, that this should work. But then there is the obvious question of can you do like the whole identity block when you can have multiple graviton exchanges, et cetera, which to me sounds potentially much more complicated. But okay, I'm not an expert on this. On the CFT technology. So if people have good ideas of how to improve and push this further, I'd be very interested in learning about that.
Okay, thank you. Samir, you still have your hand up. Is that a random, or you want to ask another question?
No, I think that's from before.
Oh, okay. Yeah, in any case, does somebody else have any more questions? Feel free to jump in.
I just wanted to mention one point in response to Emil's question. I don't know if this is relevant, but I think in the earlier computations of Roberts and Stanford, where there was there was just one temperature, not two temperatures left and right. Then there, I think they were assuming the sigma to be positive. So that's why they just get the exponential t minus sigma. But if one was taking the spatial insertion point to also allow it to run to negative, then there would be like a t minus absolute value of sigma. So that's how the left or the right movers contributed in their computation.
Okay.
Okay. Thank you, everyone. If there are no more questions, let's thank